Hi, the next few tutorials are going to be about capacitors. Now, capacitors can be quite mathematical, it can get quite complicated. Uh, the important thing is the end result. So you might have some differential equations and you'll get a formula at the end of it. Well, it's the formula at the end is the only thing you're ever going to use from that point onwards. You're never going to have to do the derivation again. So if you don't follow some of the mathematics, not in this particular tutorial, but in some of the other tutorials that will start to come in now with capacitors, don't worry. Just don't worry about it. I mean, unless you're doing a university course where you have to like do the derivation, then it might be useful to you, but for everybody else it won't be that useful. So anyway, here's the first one. This is going to be an introduction to capacitance. So what I've got here is I'm just going to read these blocks and then explain the blocks. So the first block, it says two conductors separated by an air, vacuum or insulator form a capacitor. When in use, these have charges of equal magnitude but opposite type. So there's four positive charges on that side and four negative charges on that side. So the net charge for the whole component is zero, because if we look at the whole component here, then the charges are balanced. They're all balanced. So looking at the whole component, there's a net charge of zero. But the nearby separation, because these two plates here are very close, and we've got accumulation of opposite charge on each side, this is inducing an electric field, and it's this field, these charged particles want to come back together again, and that's what produces the field. So there's an attractive force between them here. So number two, the definition. So the capacitance C is defined as the ratio of the size of the charge Q to the size of the voltage between the plates, and it's a fixed ratio. So basically the C here is a fixed number for a given capacitor, and it's given as the ratio of the charge that is on the plates over the voltage between the two plates, and that's a fixed number. So if we look at block here 3, it says since C equals coulombs over voltage, 1 coulomb per volt is defined as 1 farad. So that means that 4 coulombs per volt would be 4 farads. So that's basically, we've got a new unit here called the farad, yeah. And this is a measure of the capacity of how much charge you can get on a capacitor. So here, number 4, the capacitance is only defined by the physical properties of the component. So the capacity to hold charges is defined by the physical properties of what make up the capacitor itself. The main points being, if the plate area is large, then obviously if this plate area is very large, then you're going to get more charges on them, yeah. So that increases the capacitance. Also, if this distance here is very, very small, then the electric field, remember the definition of electric field is an inverse relationship, so it's much stronger when the distance is very small, yeah. So obviously if we reduce the distance between these plates, we're going to see a much stronger electric field, and that also equates to a higher capacitance. So now, just quickly, now this is something we can go through now. It's just working out the capacitors in series. Right, I've got a very simple circuit here with 2 capacitors. The green here is representing the electric field between the plates, if you like. So there's 2 capacitors, C1 and C2. And between each capacitor, obviously, there's a voltage, and I've labelled this middle section here C. So we've got voltage AC and voltage AB, where this is B and this is A. Okay, so the voltage across C1, across these plates of C1, is the charge divided by the capacitance, and the voltage across this capacitor here is again the charge divided by the capacitance. Now the interesting thing is the charge is going to be the same, and this is the important point about series capacitors. The charge on this capacitor is exactly the same as the charge on that capacitor, because if you see that there's say here 1, 2, 3, 6 positive charges on there. For this to balance, that there'll have to be 6. You know, if you put on an extra charge on here, then this one would eventually have an extra. The charges will balance, yeah. So that means no matter how many capacitors you have in series, the charge on them will be the same. It will always be the same charge on each one, yeah. So that's important to when we just give this series evaluation here. So what we're saying is the total voltage is obviously the voltage across number 1 capacitor and the plus the voltage across C2. That gives us the total voltage across these 2 points here. So that's VAC add VAB. Now, as we've said, the charges here is the voltage using this formula, C equals charge over the voltage between the plates. We can rearrange that to get the voltage across this one is simply the charge over C1. Okay, so then using this, we can place these two in here to get this. So we've put, now, as I said before, the important point here was the charge is the same magnitude on both of these. So that means we can pull the charge outside like this, and so we've got the voltage across AB is then replacing this Q over 1CT over 1C1. So then, of course, if we divide VAB by this total charge here, then we're going to get VAB over QT, which is obviously using this again, 1 over the total capacitance. So then we see we've just manipulated these equations to get 1 over the total capacitance is 1 over C1 and 1 over C2. Now, if you had 4 capacitance, it would simply be 1 over C3, 1 over C4, etc. So this formula holds for any number of capacitors. So if you want to think about series capacitors, always use this formula. And I know often you'll see the C2 times C1 over C1 add C2. That's for two, for the specific case when there's just 2, and that's quite often handy to use, yeah. But if you forget that, then this one is applicable for any number of capacitors. So I mean, if you only remember the case of 2, which is C1 C2 over C1 add C2, then you might forget that actually that's derived from here, but it's just basic algebra, so you shouldn't really. So that's the capacitors in series. Now, capacitors in parallel. With capacitors in parallel, it's actually a lot easier than the capacitors in series, because in parallel, let's see here, we've got 1, 2, 3, 4, 5, 6 positive charges on this plate, and the opposite plate obviously has got 6 negative charges. Now here we've got 1, 2, 3, 4 positive charges and 4 balanced on the other side. So when we place this together, if you imagine that these are very, very close together, you could almost like tie these two together, and basically you just got one big capacitor, obviously. So the 6 here is going to add up with a 4 there. So you're going to get 6, 7, 8, 9, 10 on there and 10 at the bottom, yeah. And so really you can see quite obviously then that the charge on this one and the charge on that one is equivalent of saying the charges at the total charges is just the addition of both of these. So that we say again here, using this formula here, rearranging, we get Q1 equals C1 the voltage. Now the voltage obviously is the same. It's the same voltage dropped across here as across these two. Now, these two is effectively that one. So obviously the voltage is the same. So we got Q2 C1 V1 and Q2 C2 V2, yeah? So then obviously the total charge is just, as I said before, the addition of these two charges. So then we can just, using this equation, rearrange it, Q1, C1, rearrange it a bit more. So the total, obviously that's the total voltage. We can divide it through here under QT, which is obviously CT. That is CT. So then we just get down to the very simple equation. CT is C1 and C2. So here we're saying if capacitors are in parallel, then they add up. Their capacitance adds up. If capacitors are in series, then you've got like the resistive parallel type equation, yeah? Okay, one of the questions might be, when would you ever use capacitors in series? Because obviously capacitors in series, as I said, the charge on each of them is the same. So what you're actually doing is, when you put two capacitors in series, you're actually reducing the capacitance. So if these were both 100 farads each, not say 100 microfarads each, then you'd end up with CT being 50 microfarads. So you might say, well, why would you ever want to do that? Well, there is a typical scenario is when the voltage that you require in a circuit is above the actual capacitance values that you got. So you might have a requirement of, say, 80 volts, but you've only got like two 40-volt capacitors. So what you can do is you can put them in series. You're going to lose a bit of capacitance, but generally that doesn't matter because capacitance values can range. There's a wide range of different capacitance values, but there isn't a wide range of different voltage values. Yeah, so if you're running a circuit that's requiring a very, very high voltage, then you can easily get around it by reducing the capacitance. Say you needed 200 volts and you got 200-volt capacitors, then you can actually do 200 volts by sticking these together in series. So that is why you might use them in series. Very rarely is it done, but you might do it for that reason, yeah. So anyway, that's it. I mean, the most common one is the capacitors in parallel. So that's it really. So that's just a really quick introduction of capacitors. It's sort of giving you the really basics. On the next lecture we'll go into a lot more detail into this equation, and this is a really sort of static type equation. Q, remember, is the charge, so we're going to start manipulating that with the fact that current is the rate of flow of charge, and then this becomes a lot more interesting. So we'll be looking at that in the next lecture, which will be RC series circuit. Okay, thanks very much.